So I'm not Remco, I'm Lena. I'm using Remco's PC now to show you what I prepared for International K-Matrix Day. And I hopefully will illustrate some of the things Misha talked about before. Let me start my notebook real quick.
Share it.
Yeah, I will start sharing the screen. So let me start with our problem. So we have been gifted a K-matrix parameterization for 2 resonances in 1 channel because, of course, it's International K-matrix Day. The given parameter values are MA and MB, so the masses of our final state particles, the 2 resonances will eventually decay to. Then the bare masses of the resonances within the K-matrix parameterization M1 and M2, and the couplings of the 2 resonances to the channel. Now, our task is to find pole positions and the residues for the 2 resonances with our given parameter values. Okay, so therefore I prepared a Jupyter notebook. So a few words to the infrastructure I will use. Not Julia, but Python in form of a Jupyter notebook. And what is special or maybe a bit not familiar with the implementation is that I'm going to use a computer algebra system called SymPy. So in SymPy, you can essentially create the symbolic expression, which then gives you this nicely rendered LaTeX output, which is very readable for theory people, for example. What SymPy also can do is that it can simplify expressions, for example, or solve equations for you. What will happen later on is that I will convert these expressions to numerical functions to outsource my heavy computations. For this, I will use like common computational backends like NumPy, or you could also use JAX, but I'm using NumPy here, but not too much about the details here. So also for further details, I refer, of course, to the International K-Matrix Day website. If you want to see this notebook again, or if you want to play with this notebook, you can have a look there. So I pre-implemented a few things. For example, my phase-space vector and my kinematic stuff. So what's going on here is that I assume I have an S-wave channel, and therefore I implemented the Mandelstam function, which has an analytic solution for L equal to 0. And then I also implemented the breakup momentum and the standard phase-space vector with the square root definition. So here I have a picture or a graph of the phase-space vector and the Mandelstam phase-space vector again, just to reproduce these maybe known plots from the PDG resonances to verify my implementation, but not too many details on this. Now we want to come to our problem. We now want to find the pole positions for the given K-matrix parameterization within a complex plane. Linear. So what are we going to do now? We are now going to construct our T-matrix for 1 channel and 2 resonances. For this, I will define some matrix symbols. This I will do like this. So these are SymPy matrix symbols. I'm defining my K-matrix symbol. I am defining my Roche Mandelstam symbol, and I'm defining the identity matrix. My dimension is n equal to 1, so I only have 1 channel here. Okay, so matrix symbols. Nice. Now we want to construct a T matrix from the K matrix symbols. And this I'm going to do like this. So I'm first defining the first sheet now. It's T1 is equal. So this we saw before. 2. Now we have identity minus. Okay. K rho CM times, this is wrong, so autocomplete doesn't work here, but yeah, times K. Cool. And I'm missing the inverse here, as I see. Okay, so now my T matrix or my T function for my first sheet is done. Here I'm using the Mandelstam phase-space vector, and I think I'm missing an I here, so I will add an I. This. Okay, not defined. Maybe I should run the cells above. Cool. Yeah, now it's working. Nice. So I have constructed the T matrix now. I can also print out the expression with SymPy here. For example, now I print out T1. And here I have my nicely rendered LaTeX expression. So the same thing I can now do for my second sheet. This I will copy paste real quick. Just for information, as Misha told you before, I'm constructing the second sheet now by adding up the difference, so the discontinuity across the branch cut. So this 2 I row factor here. And for 2, I'm taking, of course, the inverse here. So I calculate the first sheet from the second sheet by adding up the discontinuity of 2 I row across the branch cut. Important thing is here that now row is not a Schumann-Stamm phase space vector. It's essentially the square root definition here we defined before. Okay, now let's run the cell. Okay, looks good. And what I can do now with SymPy is that I can substitute my parameterization for example, K or row explicitly here into this matrix symbol expression. So I will define a few symbols in SymPy. So here I'm defining S, so center of mass energy, the couplings G1 and G2, and the masses for resonances M1 and M2, and also our final state masses MA and MB. So symbols defined, cool. Now, what I'm going to do now is to explicitly define my K-matrix elements. Okay, this you can see here. So this is my definition for the K function for one channel and 2 poles. So the 2 terms here are equivalent to one of the poles. Essentially, here my Schumann-Stamm phase space vector is defined, and here my normal square root definition phase space vector is defined. Okay, cool. Can you see the expression now? Now let's substitute in these expressions explicitly into our matrix expressions here we defined before. So this looks kind of correct, I guess. So looks good. This is nice to verify here. So if you derive this on paper, for example, you can compare. I'm also doing this for the second sheet. My description is a bit messed up here, so I will quickly drag this up. So let's run it for the second sheet. And then nice, I have the definition of my second sheet, so the T function for my second sheet. So now we want to put in some explicit values. I will define now a set of parameters which were gifted to us, of course, before. These are the parameters. Again, these we already know. And now I'm creating a numerical function from my symbolic expression. So I'm creating a T1 function and a T2 function. So first Riemann sheet and second Riemann sheet, like this. So what's happening here is that from this expression, a numerical function gets created with the given parameters which I defined here. Okay, I have my numerical function now. Now I can plot my numerical function. This I also prepared. What I'm going to do now is, I will show you, I will plot the absolute square of the second Riemann sheet, I epsilon, so like a tiny bit off of the real axis here in the lower part of the complex plane. And what I can see here now is, okay, nice, I have 2 peaks here as expected. So I would expect this because I have 2 poles given in my parameterization. So it looks kind of as expected here. What I can also plot is a 2-dimensional plot. I will do this real quick. Of my 2 Riemann sheets. And now this looks a bit nicer. So what we see here is the real part of S versus the imaginary part of S, and the magnitude here in color represents the imaginary part of the transition function. So the T function or the T matrix function. In the upper part of the complex plane, we have T1, so the physical sheet, and in the lower part, we have the unphysical sheet defined, which, as we see here by these like funny, dots here, we have the 2 poles we expect there. So what we can also see here is that the second sheet nicely and analytically continues to the first sheet here. So the transition here is very smooth. Okay, now we want to find the pole positions explicitly. So we have this picture, but now we want to kind of calculate it. And what are we going to do now? So you might remember that we defined our T2 expression, this one here. So when does this here have a pole? This is basic analysis. So this expression explodes if the denominator here goes to 0. So what I essentially want to do is to find the zeros of this denominator here. And then I have the position, so the S, where, yeah, this function explodes, and therefore I have my pole position. What is nice about SymPy is that I can extract denominator and numerator symbolically here. Yeah, nice. And there I have my denominator. Yeah, so I will quickly make a numerical function out of this to outsource the heavy computations, and now I have it. So this whole problem here to set this thing so the denominator 0 is a gradient descent problem. So I will use a maybe familiar minimizer called min2 to extract, yeah, the zeros here. First, maybe we plot the denominator. So I will plot this function here basically first to verify that these pole positions really are equivalent to the zeros in the denominator. Okay, cool, looks good. We see here, so this is a logarithmic scale, but still we see the same things. The magnitude in color is equivalent to the denominator function TS. And here again, we have real and imaginary part of S. So we can compare the two plots now, and we see here, okay, we have 2 points where this gets very, 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 very small. So basically 0. And therefore, we should be expected to find 2 pole positions. Okay, back to finding the pole positions. So as I said before, I will use min2. What do I need to use min2? So I need an initial guess first to start min2. And I need a cost function to minimize. For the cost function, I will pick the denominator function, but the absolute squared of this. And for my initial guesses, I'm just looking at this plot here where, yeah, roughly these zeros are located. Doesn't have to be that precise, but a good initial guess is always better. I prepared these, so by eye measure, I see these numbers here. Yeah, and then I can define my fit function. So first I will define my cost function. So basically the function I will put into min2. What I'm doing here is I use the denominator function, so the absolute square of it. And what's important here is that I'm splitting S into real and imaginary part, because min2 can only handle real and imaginary part of a number separately. So just to make this function accessible for min2. Then I will define my minimizer here, put it here. So here my min2 is defined. I will use migrate. And now what I can do is that I can, yeah, fit these pole positions with my initial guess. So let's fit the first pole. Yeah, maybe I do this. Let's fit the first pole. Okay. Maybe I should run the cells again. Okay, nice. Seemed to work. And then I can print out the pole positions min2 found. Okay, cool. Looks kind of good, kind of close to my guess, but let's see later. I will quickly fit the second pole. Okay, also nice. So let's first plot the values Minuit found here. So the two complex numbers. I will do the same plot I did before. So this one here. And as you can see here, so these red X's mark the pole position Minuit found in my plot, basically. So you can see here, okay, by looking at it, Minuit found like reasonable pole positions for, yeah, our problem here. So this is good. This is how you find a pole. What we want to do now is to compute pole residues. So I skipped a few cells, but let's come to the pole residues. So what we want to do next is to find the residues, and these can be computed, as Misha also mentioned in his talk, by a closed contour integral around the pole position we found before with Minuit. So the most natural choice to integrate over is, of course, a circle. And to compute this integral numerically, I just transfer the integral into sum of n points. So what is happening here? I drew a picture of this. I have my pole position here. This is what Minuit found for me. And then I'm doing a closed circle around it. And I split this contour into n points, as you can see here. Here is the formula I used for finding the residue. And now let's define this formula in code. Okay. Okay, here I define the formula I wrote here in LaTeX. So this should be fine now. And then I can compute the residues for the first and the second pole. So residue 1 is then this one here. So I'm using the T1 func in this case. And not the T1 func, I should use the T2 func because the poles are located on the second sheet. And pole 1 here is defined as my first pole position computed by Minuit. So here, this is the complex number I'm giving to the compute residue function now. And yeah, seemed to work. So now I can print it. Okay, it found something, at least. I can do the same thing for the second pole. So again, I'm giving the function my T2 function where the poles are located on, and I'm giving at the point Minuit found where the pole should be located. So residue 2 found. Okay. Nice. Now, what to do with these residues? So Misha, I think, told you before in his lecture that in my case here, the residue approximates the coupling of the poles if they were to be considered as single poles, for example, in a Breit-Wigner parametrization. This I can then verify. So here you can see my T function at the pole position itself is then approximately the residue, so minus the residue, over this denominator here, which is Breit-Wigner parametrization. And therefore, I can say, okay, my pole coupling, so the coupling at my pole position is roughly the square root of my residue. Okay. So first, I will compute the pole coupling from the residue, not to be confused with the G couplings I put in before. So to parameterize the K matrix, these are really the couplings at the pole position, so the pole couplings. Okay. And now I can define my Breit-Wigner at the pole position. I just, wrote this formula here. And then I can plot everything. So let me just copy and paste the plotting infrastructure. First, let's plot what we already know. I'm commenting this out. Okay. Oh. Okay, so see. So I want to show the plots, not all at the same time, but in a row. So first, we see here what we already know. We see the t function here in blue. So this is yeah, the function of my first Riemann sheet. So the line shape we see, so this projection on the real plane. So this looks like the line shape we saw before. And then I can see here the sum of the two Breit-Wigner parameterizations for pole 1 and pole 2. So the sum of these with the couplings estimated as the square root of the residue I found with my closed contour integral. So these look very much the same. And what I can also plot then is each of the Breit-Wigner parameterizations separately, so as if the poles were to be considered as single poles in a Breit-Wigner. And then I can see these ones here. So just to verify, it now becomes clear that essentially my residues are equivalent to these pole couplings. So the square root of the residues is equal to the pole couplings as if the poles were to be considered in a single Breit-Wigner parameterization. So I think this was everything. So I only looked at the one channel case in this example. We also have implemented the two-channel case. This can be found on a website as bonus material, but I think two channels would be a bit too much to go into detail in one talk in only like 40 minutes or so. So I encourage you to look at the website, and if you want to know more about the infrastructure we used, you can also look this up on the website. So then thank you for the attention.